In this video, we're going to look at the structure of the periodic table and some ways that we can organize it. First, we want to look at two historic scientists who contribute to our current understanding of the periodic table, as well as a couple of historic periodic tables. The first scientist is Dmitri Ivanovich Mendeleev, a Russian chemist working in the late 19th century. He's credited with the creation of the first periodic table and really began to notice some periodicity in the organization of the elements. We'll come back to that term later. Mendeleev's periodic table needed a little bit of revision, and that came with the work of Henry Moseley. Moseley is a really interesting historic character, and we'll talk more about him later. Here's an example of Mendeleev's, one of his earliest tables. Mendeleev began by taking the properties of all the different elements and writing them down on index cards, and then arranging those index cards into different patterns. What he noticed is that when he began putting properties such as the number of oxygens that an element binds with, the number of chlorines an element binds with, or maybe the melting point of an element, he was able to arrange them in such a manner that there was some periodic property, or that certain properties appeared regularly or periodically. His table doesn't look a whole lot like the one we recognize today, but you can begin to see some familiar arrangements of elements, carbon, nitrogen, oxygen, fluorine being next to each other. And you can also begin to see some of the elements that we see on the left side of the table arranged horizontally here. These are some of the earliest patterns that Mendeleev noticed, and he was able to predict the presence of other elements despite not knowing that they were actually there. For instance, these elements were unknown in Mendeleev's time, but the gap that they had on the periodic table, or the gap that they represented on the periodic table, indicated to Mendeleev that they had to be there. Here's a periodic table from 1905, and it just looks a little bit more like the one that we're used to seeing, although still quite different. Again, here's another example of a periodic table. This one just sort of a cartoon representation, but it gives you an idea that in Mendeleev's time there were some missing elements. And again, if Mendeleev was able to arrange his elements, when he arranged his elements in terms of, say, their melting point or their boiling point, he noticed some gaps where there should be some additional elements. And Mendeleev is in fact credited with predicting the existence of several elements before their eventual discovery. He didn't have names for them. He wasn't able to isolate them. He didn't know exactly all of their properties, but based on gaps in the periodic table, he predicted there had to be some missing elements there. And that was really what sealed the power of this periodic table. Its predictive ability to predict the existence and actually accurately predict the existence of some missing elements. Here we have sort of our modern view of the periodic table, and it's color-coded. We'll talk about what some of those colors mean in just a moment. And we'll begin looking at some general ways we can arrange the periodic table. One really good way to organize the periodic table is in terms of the metallic character of the elements. And you notice that the vast majority of the elements are classified as metals. That is to say, they have strong metallic character. So we want to write down a couple of different properties of metals. Metals tend to be hard. They tend to be shiny. They tend to conduct a current. Metals are also what we call malleable. That is to say, you can bend them or you can rearrange them. And many of them are ductile. That is to say, they can be drawn into a wire. Finally, metals tend to have a high melting point and a high boiling point. So looking at our properties of these metals, you might recognize a lot of the metals that or a lot of the elements that are classified as metals on the periodic table. Here's iron, for instance. Here's copper. Here's zinc, aluminum. So a lot of really familiar metals on there. There's a lot that might be less familiar to you. Barium, for instance, strontium, less common metals, or yttrium. But again, to a certain extent, those all exhibit the properties of metals. On the other side of the table, on the right side of the table, we have the nonmetals. And those are characterized by sort of what they're not. That they tend to be dull. They tend to not conduct a current or not be conductors. They tend to be brittle instead of malleable. And they tend to have a low melting point or a low boiling point. think it's also interesting to point out that most metals are solid at room temperature. Mercury is an exception. It's a liquid. Our nonmetals tend to be liquids or gases. In fact, mostly gases at room temp. And finally, you notice that we have a few elements that are right between the metals and the nonmetals. Those are the metalloids. And you can guess that the properties of those are sort of halfway between metals and nonmetals. And the number of properties they have is of one or of the other, varies a little bit from element to element. But you can imagine that some might conduct a current but be brittle. Others might be dull but malleable. There's some shared properties in there. We might recognize silicon or arsenic as maybe two of our more famous metalloids. So metallic character is one way that we can organize the periodic table, and it's a really good way. And I think the take-home message here is that most of our elements are metals. That's something important to remember. Here we have a blank periodic table, and we're getting into a little bit more detail about ways that you can organize the periodic table. First, I want to talk about periods, and those are the horizontal rows going across the table. Those are these horizontal rows here. So periods we can also call rows. And a periodic relationship, and that's what I mentioned earlier, is that properties, there's similar properties, appear periodically or regularly across the table. Let's take a look that if your property, let's say maybe you have a property of binding with 4 hydrogens. Carbon binds with 4 hydrogens. That's right here, this element C. So we can envision that periodically, as we sort of go across the table, that silicon will also bind with 4 hydrogens. And as we go across the table, germanium will also bind with 4 hydrogens. And as we go across, tin will also bind with 4 hydrogens. So that's what I mean by periodic, or a periodic relationship, that elements that are in the same column or that appear at regular intervals share a lot of properties in common. And those are the ways we maybe want to classify this table. So we call groups or families, those are the columns on the periodic table. Columns of elements. And these tend to have properties in common. Have properties in common. So let's look at a handful of these groups on the periodic table. We'll start with the alkali metals. These are our alkali metals here. Hydrogen, despite being in the column of the alkali metals, actually behaves quite a bit differently and is not going to be classified as an alkali metal. So here's our alkali metals, and I want to list a few different properties of these metals. These are highly reactive. They're not found alone in nature. That's because they're so reactive that they're already going to bind with something. They tend to lose 1 electron to get a +1 charge. They tend to be pretty soft. Things like lithium, sodium, potassium, you can really sort of manipulate those without too much difficulty. But I want to stress that they're highly reactive, so these are not things that you want to be handling because any water in your hands might react with them. Right next door to the alkali metals on the periodic table are the alkali earth metals. And this starts with beryllium, magnesium, calcium, strontium, barium, and radium. And these are also pretty reactive, but a little bit less so than the alkali metals. These typically are not found alone in nature. That is to say that you won't find a lump of calcium or a lump of magnesium just lying around. Those things need to be purified. They tend to lose 2 electrons to get a +2 charge. We'll talk more about ions later. And these also tend to be pretty soft. So just some properties of alkali earth metals. Look at our halogens. Halogens right here: fluorine, chlorine, bromine, iodine. Astatine is incredibly radioactive, and there's very, very little astatine. It's incredibly rare. So while it is a halogen, we almost will never see it in this class. So halogens, those are also reactive. But these actually will gain 1 electron to get a -1 charge. Halogens tend to be poisonous. You think about where you see fluorine, you put it in toothpaste to kill bacteria in your mouth. Chlorine is put in a pool to kill bacteria and purify that water. Bromine or iodine you maybe put on cuts to disinfect them. So these things are poisonous to bacteria in small amounts and actually poisonous to humans in large amounts. Chlorine gas was used during World War I with pretty deadly effect. And halogens can be in all sorts of different states of matter at room temperature. Iodine's a solid, bromine's a liquid, chlorine and fluorine are gases at room temperature. Right next door to the halogens is another interesting group of elements. These are the noble gases. They're called noble gases because they don't react with other compounds. That is, they're sort of noble, or they sort of stay themselves as if they were sort of the nobility of a society. These noble gases, things like helium, neon, argon, are very unreactive. That is to say, they do not form compounds. They're all gases at room temperature. And there's not a whole lot else to say at this point. We'll come back and we'll see the noble gases a little bit more. We're going to talk about the number of valence electrons they have. But that's a new term, and I'm not sure I want to go into a whole lot of detail about that here. But I suppose if you want to put it in the back of your mind, you could say that these noble gases also have a full valence shell. We'll talk about what that means later. Lastly, we have the rare earth metals, and I think I've run out of highlighter colors. Let's see, actually I have an orange. These are my rare earths. And I think the important thing to say about the rare earths is they're not especially rare, but they're really hard to isolate. And that's why they were called rare for a long time, is we had a hard time separating one from another. These are actually really important for magnets and for electronic equipment and for electronics. So things like your iPod or a car are going to have a lot of these rare earths in them. And these are interesting in that they're sort of a geopolitical interest where China controls a large percentage of the world's supply of rare earths, and has sort of sole distribution and mining control over them, which just presents some interesting sort of leverage in trade negotiations when it comes to things, again, like magnets or electronics, which are everywhere now. So these are two different ways that we can organize the periodic table, both in terms of metals or non-metals, or in terms of different groups. And you notice that not all of our elements are assigned to different groups. There's not necessarily names that I want you to know for, say, iron, ruthenium, and osmium. One other thing I would point out about the periodic table is uranium is our largest naturally occurring element. So from neptunium on, these are all artificial elements. And again, not a group name. They don't stick around for very long, but I think an interesting thing to point out. They're artificial elements. So that's going to wrap up our conversation about the periodic table for right now, and we'll do some more work getting ready and learning about it.